Okay, so hi everyone, another day, another dollar. You can tell it's a new day because I'm wearing a different shirt, but anyway. So, we looked last time at gravitational forces. Now what we're going to be looking at are gravitational fields. And when we talk about fields, we're talking about a region around an object which can exert a force on other objects. So, you'd be familiar with magnetic fields. If you've got a magnet, you can place certain objects a bit of a distance away from them, and there's going to be some force on that object because of the magnetic field. So we're talking about something similar when we're talking about gravitational fields. An object with mass produces a field around it. Other objects with mass that get placed near it are going to be affected by that field. They're going to have a force acting on them because of that field. So that's what we're talking about when we're talking about a field. Something surrounding an object that can exert a force on other objects. Now when we talk about fields, we can represent them using what are called field diagrams. I've drawn one down here. So we've got an object, circular one, with some mass, and I've drawn field lines around it. Now, when we're talking about gravitational fields, we're talking about something called a radial field. We're talking about the field lines are all pointed in towards the center of the circle. So we've got those. We've also got the case that, well, one of the things that field lines show us is how strong the field is going to be. So if we have a look at the area close to the object, the field lines are going to be closer together than when we move further away. So here, we've got the field lines closer together. That indicates that the field is going to be stronger in these locations. The further away we get, the further apart the field lines are from each other compared to when we're in closer. That implies that the field is going to get weaker as we get away from the center of the object. So the field lines indicate a few things. One of those is just going to be how strong the field is. The closer the field lines are, the stronger the field is going to be at those locations. So the more force there would be on an object put here compared with out there. We've also got arrows on our field lines. These are all pointing towards the center of the object, if you see those. What we take away from this is that when we're dealing with gravitational forces, we're dealing with attractive forces. We're dealing with forces that are going to pull two things towards each other. When we look at things like electric and magnetic forces, we can also get repulsive forces, two things pushing each other away. But with gravitational forces, it's always an attractive force. There are no repulsive gravitational forces in nature, so our field lines for gravitational fields are always going to point towards the object. This object's field is always going to be pulling other objects towards it with its gravitational field. So that's what our field lines tell us, direction and strength. That's what you need to know about those. Now, move this down. I think there's about the top. There we go. Oh, there's a lot down top. I have to do a bit of moving. Also move this chair out of the way. Move that. Excuse the inconvenience. And just reposition the camera. Very good. Okay, so when we talk about gravitational field strength, there's a little thing on the side of the screen and I can't tell where the other things are. Yeah, this is going to be a pain in the ass. Gravitational field strength is denoted by the little g. It's something you're familiar with. When we find the weight force, we use the letter g to represent 9.8 because that's the Earth's gravitational field strength at the Earth's surface. So gravitational field strength, how strong the gravitational field is, that just gets denoted by a little g, as you'd be familiar with. But it measures how strong the gravitational force that is acting on an object happens to be. And one way we can calculate that, the most basic way, is just rearranging that Fg equals m times g equation to get g on its own. So what the gravitational field strength tells us is how much gravitational force there is acting on an object of mass m. Now, this equation, you'll use it sparsely, maybe. This is really just a stepping stone for the next part. And I'll just mention quick that g has units of newtons per kilogram. This has units of newtons. That has units of mass is kilograms. So newtons per kilogram. That's where we get our units of gravitational field strength from. But from yesterday, we also know that the gravitational force between two objects is going to be given by this equation. Yesterday I had m1 and m2 because we were interested in calculating the gravitational force between two objects, and that was going to be symmetrical because, well, the forces between the two objects due to the gravity is going to be the same. But here I've just switched them over. Hopefully this comes through clearly. I've made this into a big M and this into a small m. Now, the reason for that is going to come through in the next line. I take my equation from before, G equals Fg over m. I substitute in for Fg the value that I've got up here, and now my small m up the top is going to cancel out with the small m down the bottom. And what I get out is this equation here, that the gravitational field strength equals G big M divided by R squared. Now, when we're talking about these m's, the big M is going to denote the object that is producing the gravitational field, and little m normally denotes the object that is in the gravitational field that has some force acting on it. So, our big M is just the mass of the object producing the gravitational field, and R is, just like yesterday, the distance between the centers of the two objects. So if you're standing on the Earth's surface, it's the distance between you and the center of the Earth. That's what your value of R would be. Now I'm going to move this up a bit and just go through a quick example. Weird camera. The question is asking, what is the gravitational field strength 8 times 10 to the 6 meters from the Earth's center? So I can just plug numbers in to my value for the gravitational field strength. I've got a value for big G from yesterday, the gravitational constant of 6.67 times 10 to the negative 11, and then it's got its units, but I'm not too concerned about those. Mass of the Earth is the same today as it was yesterday, I'm assuming. That's 6 times 10 to the 24 kilograms, and my distance to the center of the Earth, as it says in the question, is 8 times 10 to the 6. So I have to remember to square that as part of my calculations. And if I do that, I get out 6.25 newtons per kilogram. That's a reasonable number to expect. If I was exactly at the Earth's surface, which is 6.4 times 10 to the 6 meters from the center, if that was my distance, then I should get out exactly 9.8. I won't do that because that would require me to write whatever. But if I was at 6.4 instead of 8 times 10 to the 6 meters from the center of the Earth, this should come out as 9.8 newtons per kilogram, the value for the gravitational field strength that you'd expect at the Earth's surface. Because I'm further away from the Earth's surface when I'm at this distance, I'm going to have a weaker gravitational field strength. Not too much weaker, a bit weaker, because I'm not so far away from the Earth that gravity is going to become minuscule. It's going to be a bit weaker, 6.25 contrasted with 9.8. So this seems like a reasonable answer for me to expect. It's smaller, but it's not minuscule and so small that it's ridiculous. So this is the first part of the video. There will be more to come.